Your 8-year-old asks if they can design their own toys. You say yes, expecting crayons. They open Tinkercad and model a robot arm with moving joints. 2 hours later, you're knee-deep in research because this just became real. I'm Rajiv Patel, and I've spent the last 3 months testing machines against real elementary skill levels and running 4 of them through my own household's gauntlet. You're listening to the STEM Lab podcast. Quick heads up before we get rolling, everything you're about to hear, the research, the data, the testing protocols, all of it is human verified and written by a real author. The voice you're hearing, though, that's AI generated. Just want to be upfront about that. If you've been listening to this show for a while, thank you. Seriously, it's great having you back. If you're new here, welcome. We release new episodes every Monday, Wednesday, and Friday, and we focus on STEM learning aids, toys, and tools that actually hold up under real-world use. Today, we're talking about beginner 3D printers for elementary students. So let's get into it. The market's packed with dozens of machines claiming they're kid-friendly, but most either lack the safety features you'd need for unsupervised use, or they demand technical troubleshooting that's way beyond what elementary students can handle. I evaluated 17 models and put them up against the kind of requirements you'd see for entry-level CAD jobs, then watched how they actually performed with kids ages 6 to 12. 6 of them stood out with clear value for building real industry-standard skills. Now, let's talk about what actually matters when you're choosing one of these printers. First up, print volume versus footprint. Elementary-age kids need machines that fit on a bedroom desk without taking over all the space they need for other activities. Build volumes between 100 and 150 millimeters cubed give you enough capacity for about 90% of elementary projects. We're talking chess pieces, simple mechanisms, prototyping iterations, that sort of thing. And they stay compact, under 400 millimeters per side. My own testing backs this up. Kids ages 6 to 9 rarely design objects that go over 120 millimeters in any direction. They don't have the patience for 8+ hour prints, and honestly, they benefit way more from being able to iterate quickly. Printers offering 200 millimeter plus build volumes sound impressive, sure, but they create 2 problems. 1, longer print times that blow past elementary attention spans. 2, they're physically larger and they dominate home learning spaces. There's an exception, though. If you're planning to integrate 3D printing with robotics projects, you'll benefit from 150 millimeters or more to accommodate chassis components. Next, enclosed versus open frame safety. This decision directly impacts how much supervision you'll need and where in the house you can actually put the thing. Enclosed designs prevent mid-print contact with moving parts and hot surfaces, which means you can allow limited unsupervised operation once the initial setup's done. Open-frame machines cost less, but they demand continuous adult presence. The moving print head operates at 200 degrees Celsius, and curious siblings are a constant risk factor. I let my own children initiate prints on enclosed machines after they run through verification protocols. Then I check progress every 20 minutes. Open-frame models, I have to be in the room the entire time. For a detailed look at safety trade-offs and performance, we've got a full enclosed versus open-frame comparison, covering thermal consistency and injury prevention data across 12 models. Moving on to software. Elementary users need browser-based slicing interfaces with visual preview systems. No command line operations, no manual G-code editing, no firmware compilation. The best candidates offer direct integration with Tinkercad and Fusion 360 for education, so there's workflow continuity from design to fabrication without file format conversion errors. The machines worth investing in provide a 3-tier progression. Simplified one-button interfaces for grades 1 through 3, intermediate parameter control, things like layer height and infill density for grades 4 and 5, and full manual override for grades 6 and up when users are ready to troubleshoot failed prints on their own. This mirrors actual professional CAD to manufacturing pipelines, where junior engineers operate within established parameters before they earn advanced access. Software subscriptions are a hidden cost, so prioritize models that offer lifetime access to slicing tools rather than annual licensing schemes that inflate total ownership way beyond the initial purchase price. Then there's filament compatibility and material costs. PLA filament is the industry standard for elementary applications. It's biodegradable, low temperature, extrudes between 190 and 220 degrees Celsius, has minimal warping, and it's available at $18 to $22 per kilogram from multiple manufacturers. Printers that require proprietary filament cartridges or RFID chipped spools create ongoing consumable costs that average 40 to 60% above commodity PLA pricing. My household consumption data shows elementary users burn through about half a kilogram monthly during active learning phases. Proprietary systems add $120 to $180 annually versus $100 to $130 for open source filament compatibility. Make sure the model accepts standard 1.75 millimeter filament from any manufacturer, rather than locking you into single-source supply chains. We've got a comprehensive filament types breakdown, covering thermal requirements and safety considerations for PLA, ABS, and PETG. Bed leveling automation is critical. Elementary users don't have the fine motor precision and diagnostic experience to manually adjust bed leveling across 4 corners while measuring 0.1 millimeter gaps with paper shims. Automatic bed leveling via inductive sensors or pressure switches eliminates the primary failure mode that causes 60 to 70% of beginner frustration. Machines offering manual-only leveling require adult intervention before every print session, which undermines independent operation and transforms the printer into another device children have to request permission to use. My testing protocol involves deliberately de-leveling beds by 0.3 millimeters, then watching whether children ages 7 to 11 can successfully initiate prints without help. Manual systems failed this test universally. Auto-leveling models succeeded 80 to 85% of the time after initial orientation. That 15 to 20% failure rate mostly comes from depleted bed adhesive that needs reapplication, which is an acceptable maintenance task. It teaches consumable management rather than complex mechanical calibration. Let's cover lab specs: power, connectivity, and expansion. Power consumption ranges from 80 watts for compact enclosed models to 200 watts or more for open-frame designs with heated beds operating at 100 degrees Celsius. Elementary installations should prioritize USB connectivity and SD card operation over Wi-Fi dependent systems that introduce network configuration complexity and potential security vulnerabilities on home networks. Cloud-dependent slicing platforms become unusable during internet outages or when services discontinue. We've already seen 3 consumer 3D printing platforms shut down since 2023, bricking hardware that relied on cloud processing. Expansion compatibility matters for 10-year-plus users. Can the machine accept upgraded extruders? Do third-party nozzles fit? Is the control board flashable with custom firmware? These factors determine whether the printer grows with advancing skills or becomes obsolete when users outpace factory capabilities. We've got a complete 3D printing station checklist covering ventilation, storage, workspace organization, and electrical and safety compliance. All right, here are the 6 printers that came out on top. The FlashForge Adventurer 5M delivers fully enclosed construction with HEPA filtration, automatic bed leveling, and a flexible magnetic print surface that pops completed models off with minimal force. You eliminate the scraper tools that represent injury risks for younger users. Build volume of 220 by 220 by 220 millimeters accommodates 95% of elementary projects, while keeping a footprint under 450 millimeters per side. The 4.3-inch touchscreen interface operates via icon-based navigation that requires 0 text reading. My 6-year-old successfully initiated prints after watching a single demonstration. FlashForge's slicer software runs browser-based with direct Tinkercad export, so you get seamless design-to-print workflows without file format gymnastics. Check the link below to see the current price. On the plus side, the HEPA filtration system makes bedroom placement viable without VOC concerns. The magnetic flexible build plate requires no tools for print removal. There's a built-in camera that enables remote monitoring via smartphone app. Filament runout detection pauses prints automatically to prevent failures. The enclosed chamber maintains consistent temperatures for reliable PLA adhesion. You've got USB-C and Wi-Fi connectivity with offline SD card backup operation, plus direct integration with Tinkercad via cloud partnership. On the downside, the proprietary filament detection system limits third-party spool compatibility to 1 kilogram sizes. The touchscreen interface occasionally lags by 2 to 3 seconds during rapid menu navigation, and the camera resolution at 1080p is insufficient for detailed layer inspection from mobile devices. Next is the Creality Ender 3 V3 SE. This represents the budget entry point at price ranges typically under $200. It offers CR Touch automatic leveling and a 220 by 220 by 250 millimeter build volume in an open-frame Core XY design. This machine requires adult assembly, about 90 to 120 minutes following included instructions, but it creates valuable mechanical exposure for students in grades 4 and up. They observe belt tensioning systems, stepper motor installation, and electrical connections that demystify how motion control systems function. The Ender 3 ecosystem includes thousands of community-generated modifications and upgrades, positioning this printer as a long-term platform rather than a sealed appliance. Check the link below to see the current price.
The positives. Open-source firmware, Marlin, allows custom modifications and third-party upgrades. The direct drive extruder handles flexible filaments beyond basic PLA. Community support provides troubleshooting resources across Reddit, YouTube, and forums. Standard V-slot extrusions enable mechanical component replacement from multiple suppliers. Print speeds up to 250 millimeters per second reduce iteration time for rapid prototyping. There are no proprietary consumables. It accepts any standard 1.75 millimeter filament, and the assembly process itself builds mechanical literacy and system understanding. The negatives. Open frame design requires continuous supervision during operation. Manual filament loading demands fine motor skills that are challenging for users under age 8. The Bowden tube configuration occasionally causes stringing on retraction-heavy models, and bed adhesion is inconsistent without supplemental glue stick or painter's tape application. The Anker Make M5 prioritizes print speed with specifications claiming up to 500 millimeters per second maximum velocity and 2,500 millimeters per second squared acceleration. In real-world terms, elementary projects complete in 30 to 50% less time than conventional machines. The enclosed design includes active noise reduction measuring 48 decibels during operation versus 58 to 62 decibels for comparable open-frame alternatives, so you can place it in shared living spaces without disrupting homework or conversation. Anker's smartphone app provides real-time monitoring with AI-powered failure detection that pauses prints when spaghetti failures begin, preventing wasted filament and unsupervised fire risks. Check the link below to see the current price. What works well? High-speed operation maintains print quality while reducing project duration. The AI monitoring system detects layer adhesion failures within 5 to 10 layers. Integrated LED lighting improves visibility for quality inspection mid-print. The magnetic PEI build surface requires no adhesives or surface treatments. One-touch auto leveling completes in 90 seconds without user intervention. You get direct Wi-Fi connectivity to AnkerMate Cloud for remote monitoring, and tool-free nozzle replacement simplifies maintenance procedures. What doesn't? Cloud dependency limits functionality during internet service interruptions. Proprietary slicer software is required for advanced speed profiles. High acceleration generates visible ringing artifacts on thin-walled prints, and the Wi-Fi setup process requires a smartphone app rather than direct browser configuration.
The Bamboo Lab A1 Mini delivers professional-grade features in a 180 by 180 by 180 millimeter build volume. You get a fully enclosed chamber, automatic filament detection, and multicolor printing via AMS Light accessory. The integrated vibration compensation system actively measures resonance frequencies and adjusts movement patterns in real time, eliminating the ringing artifacts that plague high-speed competitors. Bamboo's slicer inherits professional CAD workflow conventions, so children using this system develop competencies directly transferable to industrial Simplify 3D and Prusa slicer interfaces, rather than learning simplified tools they'll later abandon. Check the link below to see the current price. The advantages: multicolor capability with the AMS Light add-on enables complex educational models. A force sensor replaces traditional bed leveling with pressure-based first-layer calibration. Carbon fiber rods reduce weight and enable 500 mm/s speeds without quality loss. LAN-only mode operates without cloud connectivity for privacy-conscious households. The textured PEI plate provides excellent adhesion and releases prints when cooled. There's open-source integration with Octoprint and Clipper firmware via community plugins. Silent stepper drivers measure 42 decibels, quieter than typical household conversation. The drawbacks: the compact build volume limits projects to 180 mm maximum dimension. The AMS Light multicolor system adds significant cost, typically $200 to $250 as an accessory. Bamboo Studio Slicer presents a steeper learning curve than beginner-focused alternatives, and rapid heating cycles, 180 degrees Celsius in 90 seconds, create brief high power draw spikes. The Prusa Mini Plus comes from the Czech manufacturer whose i3 series established industry standards for open-source 3D printing reliability. This semi-enclosed design includes Super Pinda automatic bed leveling and a removable spring steel sheet with double-sided texture options, smooth PEI for detailed surfaces, textured powder coat for strong adhesion. Prusa's documentation philosophy emphasizes understanding over simplification. The included handbook explains why settings matter, rather than just listing recommended values, establishing diagnostic thinking patterns applicable across all manufacturing processes. Check the link below to see the current price.
The upsides: the spring steel sheet flexes to release prints without tools or force. Power panic feature resumes prints after electrical interruptions automatically. Prusa certified filament profiles guarantee print success across 30+ material types. Open source hardware design enables complete part replacement and upgrades. Prusa slicer software provides educational annotations explaining every parameter. The 32-bit controller board supports future firmware enhancements via USB updates. And you get industry-leading customer support with 24 to 48-hour response times. The downsides: semi-enclosed design leaves the front and sides open during operation. The manual filament sensor requires tension adjustment for reliable detection. The LCD interface uses rotary knob navigation, which is slower than touchscreen alternatives. And import lead times occasionally extend 4 to 6 weeks during high-demand periods. Finally, the monoprice Cadet targets budget-conscious households with a fully enclosed design, Wi-Fi connectivity, and assisted bed leveling at price points typically under $180. The color touchscreen interface displays real-time print progress with filament estimates and completion time predictions that help elementary users understand resource planning. Monoprice's target market position accepts compromises in print speed and ecosystem sophistication in exchange for entry-level accessibility. This machine won't grow into advanced applications, but it delivers solid performance for grades 2 to 4 before users outpace its capabilities. Check the link below to see the current price. What's good? Fully enclosed chamber with acrylic panels provides heat retention and safety. The color touchscreen shows visual print previews before initiating jobs. Wi-Fi file transfer eliminates SD card shuffling between computer and printer. Resume print function recovers from power interruptions mid-job. The heated bed reaches 100 degrees Celsius, enabling better adhesion for larger models. Assisted leveling guides users through the manual adjustment process step by step, and the included sample PLA spool and tools reduce initial setup friction. What's not, assisted leveling still requires manual adjustment versus true automatic systems. Proprietary slicer software lacks integration with Tinkercad or Fusion 360. Wi-Fi connectivity occasionally drops, requiring power cycle resets, and the build plate coating degrades after 200 to 300 prints, requiring replacement. Let's tackle some common questions.
What age can children safely operate these printers independently? Children ages 8 to 10 demonstrate sufficient motor skills and safety awareness to independently operate enclosed automatic leveling printers after comprehensive initial orientation. That orientation needs to cover thermal hazards, filament loading procedures, and basic troubleshooting protocols. My testing framework involves supervised operation for 15 to 20 prints while children verbalize each step, then graduated independence with adult check-ins every 15 to 20 minutes during the print cycle. Younger users, ages 6 to 7, successfully initiate prints on simplified interfaces but require adult presence throughout the heating and printing phases due to burn risk assessment limitations. Open frame designs push independent operation ages to 11 to 12 regardless of interface sophistication because exposed hot ends and moving components demand mature hazard recognition. The safety threshold isn't about arbitrary age cutoffs, but demonstrated competency in 3 areas: thermal hazard identification, appropriate responses to error messages, and the discipline to not bypass safety protocols when unsupervised. We've got a complete 3D printer safety checklist covering supervision requirements and emergency procedures across age groups. How do these printers connect to design software like Tinkercad? Modern elementary appropriate printers use browser-based slicing software that imports STL files directly from Tinkercad's export function. Children click Export in Tinkercad, select STL format, then upload that file to the printer's web interface or manufacturer slicer application. Leading platforms like FlashForge Cloud, Bamboo Studio, and Prusa Slicer auto-detect connected printers via USB or Wi-Fi, eliminating IP address configuration or driver installation complexity. The workflow requires 3 discrete steps: design in Tinkercad, slice in printer software to generate G-code, transfer G-code to printer via USB, SD, or Wi-Fi. This mirrors professional CAD to manufacturing pipelines, where design software like Fusion 360 or SolidWorks outputs neutral file formats processed by dedicated CAM software before reaching fabrication equipment. Cloud-integrated systems like AnchorMake and FlashForge offer single-button workflows that combine slicing and transfer, but they create dependency on internet connectivity and platform longevity. We've got a guide to teaching 3D design skills covering capability milestones from ages 6 to 16. Do these printers require monthly subscriptions or recurring costs? The printers themselves typically require no subscriptions, but operational costs include filament consumption, averaging $8 to $15 monthly during active use, plus occasional replacement parts. We're talking nozzles every 500 to 1,000 hours, build surfaces every 12 to 18 months, HEPA filters annually for enclosed models. Proprietary filament systems, which are rare in current elementary-focused models, add 40 to 60% cost premiums versus open-source filament compatibility. Software represents the more significant subscription risk. Cloud-dependent slicers from AnchorMake and some FlashForge models currently offer free access, but include language in terms of service allowing future subscription implementation. I recommend prioritizing printers that support open-source slicers, like Prusa Slicer, Cura, or Simplify 3D. They guarantee perpetual free access, regardless of manufacturer business model changes. Realistic total cost of ownership for elementary use averages $180 to $240 annually after initial purchase. That breaks down to filament at $120 to $180, replacement nozzles $15 to $25, build surface refresh $25 to $35, and miscellaneous adhesives or maintenance supplies $20 to $30. This positions 3D printing as comparable to robotics kit investments, but less consumable intensive than chemistry lab setups requiring ongoing reagent purchases.
Can these printers handle multicolor or multi-material prints? Single extruder models, which represent about 80% of elementary appropriate printers, produce single-color prints per job unless users manually swap filament during programmed pauses. It's a technique that teaches color change planning, but adds 5 to 15 minutes per swap. True multicolor capability requires either multiple extruder systems, rare below $500 price points, or automatic material switching systems like Bamboo Labs' AMS or Prusa's MMU. These accessories add $200 to $400 to total investment and increase mechanical complexity plus failure modes. For elementary skill development, multicolor capability delivers minimal educational value. Children benefit more from understanding structural design, support material strategy, and dimensional accuracy than from aesthetic color transitions. The exception involves multi-material printing, PLA plus water-soluble PVA supports, which enables complex geometry otherwise impossible with single-material systems. But this application emerges at grades 7 to 8, when students tackle overhang angles and bridging distances requiring calculated support structures. Elementary users gain more capability advancement from mastering orientation, layer height optimization, and infill strategies on single-color prints than from chasing multicolor complexity that distracts from fundamental manufacturing principles.
3D printing bridges the gap between screen-based design work and physical fabrication, establishing CAD competency 2 years earlier than traditional curriculum timelines while building spatial reasoning skills that transfer to higher mathematics and engineering disciplines. The progression follows this pattern. Ages 6 to 7 modify existing Tinkercad models to understand dimension and transformation. Ages 8 to 9 design original functional objects, boxes with lids, simple mechanisms requiring measurement and fit. Ages 10 to 12 tackle complex assemblies with moving parts, learning tolerance stack-up and material property constraints. This timeline positions elementary 3D printing as a parallel track to screen-free coding progression. Both build computational thinking through iterative problem-solving, where failures deliver immediate concrete feedback. The skills compound. Students who master 3D modeling at ages 10 to 11 enter middle school robotics programs with the ability to design custom chassis and mounting solutions, rather than being limited to kit-provided components. This capability gap becomes visible in FRC and VEX competitions, where teams with multi-year 3D printing experience produce significantly more sophisticated mechanisms than peers learning CAD and fabrication simultaneously. We've got a robotics learning path showing how 3D printing integrates with electronics, programming, and mechanical design competencies. So, here's the verdict. The FlashForge Adventurer 5M delivers the optimal balance between elementary safe and closed operation and capability headroom for advancing skills through grade 6. The HEPA filtration and automatic bed leveling eliminate the 2 primary supervision requirements, while standard filament compatibility prevents long-term consumable cost inflation. If you're budget constrained, prioritize the Creality Ender 3 V3 SE, despite higher supervision demands. The open-source ecosystem ensures 5-year viability as children progress into custom modifications and advanced material experimentation. Avoid printers requiring proprietary consumables or cloud-dependent operation, regardless of attractive entry pricing. The devices children use today establish their expectations for how digital-physical integration should function. Better they learn on platforms mirroring professional workflows than simplified appliances they'll later need to unlearn.
That wraps up this episode of the STEM Lab podcast. Thanks so much for listening.
We're back every Monday, Wednesday, and Friday with new episodes covering STEM tools, kits, and learning platforms. If you found this episode useful, I'd really appreciate it if you'd leave a 5-star rating and write a quick review. It actually makes a difference. It's how other parents and educators find the show when they're searching for practical advice on this stuff. And if you haven't already, go ahead and subscribe or follow so you get notified the moment new episodes drop. Catch you next time.